Okay, so welcome back to another video. So in today's video we got something new here. So we have the Laplace transform of SIT of S. So SIT is actually known as the sine integral. So I'll define SIT. It's just equal to the integral from 0 to t of sine of x divided by x dx. And then the definition of a Laplace transform is basically an integral transform converting a real variable t, and we convert that into a complex variable s. So simply I'll just write Laplace and just define for some function of t. Simply it's just equal to the integral from 0 to infinity of f of t multiplied by e to the power negative s times t dt, where s is actually a complex variable. So as you can see, we're actually going to have to do basically integrals, and we're converting the finding the transform of the sine integral itself. So without further ado, so let's actually do some substitution here. So given that the Laplace transform of the sine integral of t with the function with a variable s, simply we just take that, we just use the definition of the Laplace transform, replace the f of t. So actually we'll replace this sine integral of t, we'll replace that with f of t, and we get that this is the integral from 0 to infinity of the integral from 0 to t of sine of x divided by x dx, and then multiply with e to the power negative s times t dt. Okay, and if we convert this a little further, or simplify a little further, we actually form a double integral. And then here it is, sine of x divided by x multiplied by e to the power negative s times t dx dt. So as you can see, we have our domain over here, so I'll just find this as capital D. And so this is defined as our following set. So we have that this is our x and y Cartesian coordinates over the second dimension, such that our intervals from x and y, it ranges between, so this is ranges from 0 less than or equal to x less than or equal to t, and then we also have that this is 0 less than or equal to t, which is strictly less than infinity. Okay, now what we can do is we can actually use Fubini's theorem, and with that we can actually just swap our order of integration. You want to be careful when you do this because you want to actually get your bounds right. Meaning, if we take the double integral of this, and if we were to switch our bounds, so this means we integrate with t first and then dx, but then your bounds have to switch. You actually have to change the bounds from there. When you set those two, when you evaluate those two double integrals, they're actually supposed to equal to each other. So be careful with this when you're swapping order of integration. This does not mean that 0t goes out to the back and 0 infinity goes to the front. That's not how the swapping works in this case. So you got to be careful here. If you actually manually do the swapping of integration, you actually get a new domain. So I'll just call this new domain omega, and it's defined as our following set. So we still have our xy Cartesian coordinates. This time we're actually going to have our new bounds. So we get that this is actually, it's going to be from x, which is less than or equal to t, which is less than infinity. And we get that our other bounds is 0 is less than or equal to x, which is less than infinity. Okay, good. So now I'm just going to switch to the new color. Just go back to orange. So we rewrite our Laplace transform. So t, and then, or let me write this a little better. Our sine integral respect to s. simply we are changing our bounds of integration. So this is actually going to be from 0 to infinity, and then our new bounds x to infinity of our same integrand. So, you know, the integrand doesn't change, it's just the bounds we evaluate, and the differentials just switches as well. And this time we have, this is actually going to be dt and then dx. Now, if we evaluate this further, then you'll see if we evaluate dt, then we only just focus on the exponential function over here, and sine of x over x is just a constant. So let's see, sine of x, then x, and then we take the antiderivative of e to the power negative s times t, which is basically you do a u sub. So this means we get that this is just e to the power negative st, and then divided by negative s. And then we evaluate this within our bounds of x to infinity, then dx. Let me actually just move that to the next line. Okay, if we keep going, then we just evaluate our bounds. So let's see, we get that this is sine of x divided by x multiplied by e to the negative s, substitute that in for infinity, then divided by negative s, then subtract that with sine of x, x multiplied by e to the negative s multiplied by x, then divided by negative s dx. And then we see that we plug infinity for here, so this is e to the negative infinity, so this is just 0, so this becomes 0. And then over here we have the negative s, so this is just a positive, so we get that this is just sine of x divided by x multiplied by e to the negative s times x dx. And then multiply the s on the bottom as well, or it should be good. And then I can actually factor out the s outside since this integral depends on x. So we get that this is just 1 over s, and then multiply it with our integral of sine of x divided by x, and then multiply by e to the negative x sx dx. So now how about I define this integral over here as a function in terms of s. So this means we have that I of s is equal to this integral over here, not including the 1 over s. See, so sine of x divided by x, then e to the negative x, then dx. So then this would have to mean that reiterating with our given Laplace transform is simply the following. It's just capital I of s, then divided by s. Now we're actually gonna manipulate some things. So we're actually going to evaluate this I of our function I of s that we define. But to do this, we're actually going to use Leibniz's integral rule, or in other words, use Feynman's trick. So really, I'm actually going to take the derivative of this function. Okay, so this means I take the derivative. So this is the partial derivative. See, del of s of our integral, e negative sx dx. Now, when you take the partial derivative of the integrand, we get that this is sine of x, then multiplied by, let's see, so this is using just the, what is it, chain rule over here? Not chain rule, the exponential rules. So let's see, we expect that to negative, so this is just negative x, then multiplied by e, and then negative sx, then divided by x dx. Then you can see the x's cancel out, and I'll just move the negative outside. So this is the negative integral of sine of x, and then multiply by e to the negative sx dx. Which now, as you can see, we actually have a little formulation of a standard Laplace transform. So this means this is actually the same thing as the negative Laplace transform in respect to, well, this time this is actually going to be in respect to x of sine of x and with our variable s. We know that sine of x, when we take its Laplace transform, is actually going to equal 1 divided by 1 plus s squared, so that should be a negative over here. I really should have wrote the fact that sine of x is its Laplace transform is equal to this, but I just took took a little shortcut, but that's totally fine. Okay, so now reiterate. So I'll write this. Okay, we go back to what we have. So integral sine of x, then e to the negative xx dx, which is equal to the Laplace transform in respect to x of sine of x, and then that's just equal to -1 divided by 1 plus s squared. So we have this. Now let's actually take the indefinite integral. So we're integrating in respect to s to get back our original function of I of s. So ds, then integrate, see -1, then 1 plus s squared. Then you can clearly see that this is just, this is the arctangent. The antiderivative of 1 over 1 plus s squared is just arctangent, and then negative, so s equals, so negative arctan of just s, and then plus c. Now we actually have to find our constant c. So let's go back. What if we were to plug, oh my, I almost dropped my marker, scare me. What if we were to plug s equals 0 back to here? Okay, so let's actually just go back to the red. That means if I were to plug I of 0 equals, so if I plug 0 back to the top, then we get that our integral is from 0 to infinity. Let's see, e to the negative 0, so it's just 1, so this means this is sine of x divided by x dx, which actually, this is actually known as the Dirichlet integral, and you can actually calculate this yourself. I'm not going to prove this, there's actually resources of this, but it equates to pi over 2. So if we were to set s equals to 0, so this means I were to equate, I'll put the negative arctan of 0 plus c, but you see that negative arctan of 0 is just 0, and then we get plus c, so this implies that c has to equal pi over 2. So this means so far we have I of s is just equal to pi divided by 2, and then subtract that with our arctan of s. But we can also use a little trig property to say that this is actually equivalent to just arctan of 1 divided by s. Okay, and now we're just about done. Just go back to the final. So this means I'll just save you the trouble and then just write the conclusion. The Laplace transform of the sine integral with our respect to a variable s is just equal to, so 1i of s is arctangent of 1s divided by s, so this means this is just equal to 1 divided by s multiplied by arctan of 1 over s. And there we have it in this black box. Alright, that's pretty cool if you ask me.